Hello, everyone. Thanks for coming. My name is Jiahan, and I'm a student at Cornell University. And today I'm going to talk about global instruction selection for scalable vectors. And first, excuse me. I'd like to first say why are we here and who should care about this. So the purpose of this talk is to demonstrate our support for scalable vectors in the global instruction selection framework, and we will also like to give some tips for other targets if they have similar plans. So today's talk will be covering the following points. First, I will introduce some notion about global ISL and scalable vectors, and I will introduce our implementation work. Finally, I will give a demo. Cool, and we will start with global instruction selection. It is called GISel for short, and it's a framework that provides a set of reusable passes and utilities for instruction selection. And it is global because it operates on the whole function rather than a single basic block as compared to selection DAG. And it's meant for a replacement for selection DAG. And as a matter of fact, I will give a demo to compare these two. And GISel has 4 passes: IR translator, legalizer, register bank selector, and instruction selector. And it also has some optional passes, such as combiner, which can be inserted between some passes, but we will focus on the 4 main passes. So to begin with, the first pass of GISel is IR translator, which converts LLVM IR into generic machine IR. Generic machine IR shares a similar data structure with machine IR. It is more generic because it has less constraint. As the GISel pipeline proceeds, we will constrain the GMIR finally to MIR. And the second pass is legalizer. An instruction is considered legal if the target will later be able to select it to a target-specific instruction. And in the legalization phase, we just replace unsupported generic MIRs with supported ones. And the third pass is register bank selector. It will bind generic virtual registers to register banks. And by virtual register, I mean those temporary abstract placeholders that is not yet being mapped to any physical register yet. And by generic, I mean they have not been assigned with register class constraints. And for register banks, you can just think them as a cluster of registers that share similar properties within a register bank. And the final and the fourth pass is instruction selector, where at this point, all of the GMIR will be constrained enough that it become MIR, and it would transform them to target-specific instructions. Cool, and I also like to introduce a little bit more about scalable vectors. It is scalable on top of fixed size vector because it has a constant multiple called vscale, which is unknown at compile time, and it is hardware independent, but it is fixed for all scalable vectors across the entire program. And here I would like to give a small example of a scalable vector with number of elements equals 3 and I32 element type. And we can scale it by vscale equals 1, 2, 3, so on and so forth. And next, I would like to explain our implementation work, which consists of some pre-work on parsers, machine verifier, some call lowering, and then I will explain those 4 main passes. Cool. To begin with, we have to first support the MIR to be able to parse it, and we've done that. And the next thing is that the machine verifier is updated so that we can copy from fixed size vectors to scalable ones, as long as the minimum size of the destination register, which is the scalable ones, can hold the fixed size. And it can be expressed as the following code. And after adding those support, as you can see, the MIR files are still completely generic, and we can copy between physical and virtual registers and vice versa. In the example we have shown, we can copy V8, which is a physical register, to a scalable one. And if a target wants to support scalable vectors in GISel, it has to support call lowering as well. And to be specific, they should enable passing scalable vectors as function arguments. They should be able to return scalable vector from those function calls. And they have to enable the call instruction according to target specific ABI as well. And moving on is the first phase of GISel. And since we mainly focus on ALU operations and load and stores, and these are pretty straightforward. And since we are operating on generic MIR, which is target independent, it is usually applicable to all targets. And if you want to support more opcodes, you can implement the corresponding translate opcode function in global ISL/IR translator file. And fortunately for IR translator, the things that you need to change might not be significant. Here, take an example. We just migrate to use from an unsigned type to type size explicitly, and it's done for translate the load opcode. However, legalization can be challenging because as opposed to selection DAG, which uses machine value type and extended value type, GISel uses something called low-level type, and it cannot differentiate integer types with float types. And if a target wants to support their legal types, scalable vector types, they need to map LLT to target specific vector types by using some scalar types as the building block. Here I show that how you can construct a scalable vector of scalars. You can also construct a scalable vector of pointers or booleans, etc. And you can implement the legalization logics using legalizer info with legality predicates and legality queries. And for ALU operations, they are pretty easy, and they share some logics where it is legal if the target supports vector instructions, followed by some customized target-specific predicates. But for load and store, there are some nuances. For example, we need to implement some custom logics using custom if for special cases like if you have a load store for non-standard alignments, and if the custom if evaluates to true, it will eventually invoke the customized legal load store function that you need to put your custom function implementation there. And since our work chooses to legalize instructions and types that RISC-V vector extension can support, we calculate and legalize everything based on the following map, and which is heavily relies on some notions and parameters such as vector register length, ELMO, SEW in RVV, but I won't, because of brevity, I won't dive too deep into this. The third phase is register bank selection. So intuitively, we just map scalable vectors to vector register bank. And we also need some target-specific function to map operand values to register banks using the value mapping class based on the size of the operands. And in our case, we chose to partition a single vector register bank into 4 parts based on different sizes of ELMO in RVV. And the final phase is instruction select phase. For the ALU instructions, it's pretty straightforward. Table gen just work out of the box. That is great. But for load and store, a vector of pointers, it might not be that sufficient. Because in selection DAG, pointer types are typically converted to integer machine value type or extended value type before legalization. But in GISel, we need to define some custom logic to cast pointers to SX lane. And there are also some interesting ongoing discussion regarding should we and when to introduce target-specific, quote-unquote, generic opcodes. Yes, but they are still ongoing discussions. And next, I I would like to give a demo on using the RISC-V example. So it's just A times vector, scalable vector X plus scalable vector Y. And after lowering to LLVM, I'm just showing the code for completeness, but you should really focus more on the lines in the boxes. So the first part is where we set the scalable vector stride length, and we also compute the number of remaining scalar iterations, since the total number n might not be divisible by the scalable size. And the next thing is that we splat the scalar a to a scalable vector. And here's the vector body, which does interesting real work on x times a plus y. And finally is some remaining scalar iteration and some cleanup work. And here is the lowering result from RISC-V using GISel framework in RVV, in RISC-V assembly. And here is the lowering result from selection deck. And I would like to point out some differences between them. And I will also focus on those interesting parts. And the first is the vector part. So if you remember, we first splat a scalar a into a scalable vector, but for a selection deck in the green box, it does not do any splat at all, and nor does it do add and multiply. It just do a vector accumulation and in a single operation, and that's done. But in GISel, it turns out that it translates everything literally, so it splat scalar a using V and V operation in RISC-V, and then it does multiply and finally V add with Y. And there's another point that is irrelevant to a vector, but I thought I could also bring it up, which is selection deck does some optimizations for when calculating the remainder, and GISel again translated literally again. Well, it seems like GISel is less optimized, but I guess it's just because GISel is still kind of a work in progress, and at least we have something done. But I enjoyed a lot from GISel's advantage of progressive lowering testing, where you can come up with a minimum example and just lower phase by phase, and which is relatively more difficult in selection deck. And finally, I would like to give some tips if other targets want to support it. So especially to deal with the type information. And first, use low-level types wherever you can. And you can migrate from unsigned to type size in target register info. And if you want to compare something with equals 0, use the is0 method instead. And if you want to use the greater than arrow, use type size is non-greater. And if you want to get, if you want to compare with some fixed size values, we just use get num mean value. And if you want to get the number of elements in the vector, you should switch from get num elements to get element count. And our future work is to improve the GISel framework to exploit more inter-basic block optimizations, and of course to support more opcodes as well. And last but not least, I want to give special thanks to Michael and the RISC-V team. They gave me tremendous support, and thank you.